Okay. Right. So because I got some emails about this part of the course that I think that some people are a little bit lost. So let me just give a very quick the overview or a big picture of what we're doing. So of course, in the beginning of this course, and we start with the usual standard formulation of general relativity using the tools of differential geometry. So basically, there you start with to have a good set of tools to describe manifolds, for example. But the important thing about describing manifolds, or the tool that you've learned, is that you've learned how to describe manifolds without sticking to a particular coordinate chart, right? So you're able to just use that there is some coordinate chart that you can use, and the coordinate chart might change from point to point. But at the end of the day, it's the formulation that you derive was independent of the coordinate chart that you have. Now, in this section, where we talk about gauge symmetry and so forth, this is exactly the same thing, except that there you have a notion about manifold, and it doesn't depend on how you define your coordinate system. Here, at the root of the description, it's all the same thing. It's just that you have some redundancy. You can choose a particular in the differential geometry framework. You can choose to have different. You can choose your own set of coordinates to discuss things, but the physics or the thing that is relevant is always independent of which coordinate you choose. Here, this is also the same thing, that you have gauge redundancy. And as we go along, either the equations of motions or the Lagrangian we write down are independent of which gauge we're choosing. So the different quote unquote gauges is exactly the same thing as the different coordinate charts you use. Okay, so it's always a sense of your interest. So said in another way, the reason that you feel that these things are a little bit different is precisely because the tools that you use, for example, you use differential geometry, or here we use gauge symmetry, which is actually related. These tools introduce lots of redundancy. And sometimes the redundancies are used to manifest some properties, sometimes it's used to manifest other properties. But at the end of the day, the redundancies are all removed when we talk about physical quantities. And this is what often happens in physics, which is that you have completely different descriptions of exactly the same thing based on completely different mathematical structures. But they give the same result. And the reason they gave the same result is because in some sense, the structure that you develop is a redundant structure. And therefore, sometimes this is also very useful for mathematics, because sometimes this physics will tell you that even though the setup you have a complete different mathematical system, but there's actually certain quantities in these systems that are actually mapped to each other. And therefore, if you're interested in these quantity, if there's some mathematical motivation in which you're interested in one of these quantities, you can go to the other description and try to compute these quantities in the other description. And of course, this kinds of mapping is also oftentimes useful in physics. Okay, and so that's why. So it's I always caution students about thinking about when you learn about physics and you go through a particular mathematical construction to learn how to compute things. I always caution students to never think that this is the fundamental way the theory is formulated, because you can have completely different way of formulating and getting exactly the same result. And oftentimes there's nothing that is more fundamental than the other. Okay, so let me just give a preface of this. And so therefore, I think that it's actually very nice that that we actually introduced this kind of new this other way of formulation, which is actually how people are using in some context, in some context, especially as I mentioned before, when you're talking about things which have spins. Okay, so again, so let's just go back to a little bit to review the basics. So the basic is that we have covariant derivatives. So we introduced covariant derivative which are defined as transforming covariantly under the gauge transformation. So we have this delta A, and we know that delta A will transform as exponential lambda delta A exponential minus lambda. And last time we've shown that at the end of the class, we've shown that we can define the commutator of lambda A, lambda B to be TABC delta C and plus 1/2 RABC. Where once again, your covariant derivative is written as EA mu partial mu plus 1/2 omega ABC MBC. So these are the things that we've ended last time. So let's make some, once again, let's make some comments. So first of all, of course, the important point of introducing the covariant derivative is that we have the spin connection. And the reason that the spin connection is important is because the spin connection is multiplying. So it's multiplying the generator. This is multiplying the generator of Lorentz transformation. Lorentz transformation. So in other words, so now using this covariant derivative, you can couple, so you can couple, now you can couple to any representation under the Lorentz group. Of the Lorentz group. This is very important. So if you remember that when you're doing the differential geometry, you're not thinking about anything that is not vector, that is not based on, that is not constructed from vectors. So I guess some of you might find that this is actually very similar to the differential geometry way of viewing things, where you also have something like the covariant derivative. But then depending on what you have, when you act on something, for example, when you act on a vector, then depending on what you have, then you have the derivative acting on the vector, and then you have the Christoffel symbol, right? And how many Christoffel symbol you have depends on what objects you have here, right? So, but notice that the Christoffel symbol always carries, right? Always carries vector indices. These are always vector indices. So in the differential geometry way of formulating things, you only know how to write write the action of the covariant derivative on vector-based representation. So, and what are vector-based representations? That means that you have a vector, you can have a tensor, and higher rank tensors and so forth. But these are just tensor products of vector representation. But we know in physical system, as we mentioned before, even the hydrogen atom, that you have electrons, and you have, and now we know more and more, you have neutrinos, we have quarks, and so forth. And these are not vector representations of the Lorentz group. These are spinor representation. So for those of you who are not very familiar with what I'm saying about vector representation and spinor representation, the statement is just the following. So this will be, of course, this will be the last class of this semester. So I'm going to try to fill in as much detail as possible in this class. So bear with me. And of course, because I'm wearing this helmet, so I cannot go on talking for a very long time. So this will force me to take a break every 30 or 40 minutes, which will actually probably benefit all of you. Okay, so what do I mean actually by the Lorentz group, by different representations of the Lorentz group? Remember, the Lorentz group, we define it, so a group element of Lorentz transformation, we define it as some transformation which has an exponential of a generator. So this generator, for example, we can have some transformation parameter, which is the angle times the generator. Okay, so that's what we mean by the Lorentz group. So we have this transformation parameter, multiplied by the generator. So the entire quote unquote Lorentz group is defined by this generator. This generator will take the form, must satisfy the following commutation relation, which we actually wrote down in the homework problem. Let me use flat indices instead. Yeah, so now let me just use, so let me just use flat indices and not curve indices just to be consistent. So, so let me just use flat indices. So these are the transformation parameters. So this is just like U1 rotation, where U1 rotation, your G is just exponential I theta. So this is just U1. Now you have more than one theta, you actually have 6 of them now, because AB runs from 1 to 4 and they're antisymmetric. So there's 6 of them, which represent 3 of them, of course, represents the usual spatial rotations. And 3 of them represents the 3 different Lorentz boosts. Now, of course, we need to have the Lorentz generators satisfying, so the Lorentz generators are defined that they satisfy this equation, which we've written before, AC MBD plus eta BD AC, and antisymmetric BC MAD minus eta AD BC. So you must, so the Lorentz generator must satisfy this commutation relation. Now, so when I talk about different representation under Lorentz group, of course, I've just written down the algebraic relation between these generators, that they must satisfy this algebraic relation. So different representations of the Lorentz group in this context means that different forms of MAB, MCD that can satisfy this kind of commutation relation. So the usual vector representation that you are more familiar with usually takes the form of it's going to be like a 4x4 matrix. And for example, for the rotation part, where most of you are more familiar with, the rotation part would just look like something like 1 minus 1 with antisymmetric off diagonal terms like this. And you can write 6 of these kind of matrices representing, of course, X, Y, Z rotations, and then the boost along X and Y, and then the boost along the X direction, Y direction, Z direction. And this forms a representation for your Lorentz group. And this is the vector representation. But as we see that this is, and for those of you who've taken linear algebra class, you know that this is not the only representation that you can have. There's actually something more fundamental than the vector representation, and that is the spinor representation. And that representation is defined by what is called the Clifford algebra. So this is defined by the Clifford algebra, which is just saying that you first find a series of matrices which satisfy this anti-commutation relation. So if you can find a set of matrices that satisfy this anti-commutation relation, then you can show that if you write sorry, now I'm using Crowley indices again. So let me, I shouldn't do that. So you start with the antisymmetric, so you have a series of, so let me just use flat indices. If you can find a set of solution that satisfies a set of gammas that satisfy this algebra, then you can show that if you write MAB as just 1/2 the commutator of gamma A, gamma B, then this algebra will be automatically satisfied. Okay, so this is another solution to this algebra. And things that transform, oh, sorry, I use big gamma here. Sorry about that. Should be consistent. This is little gamma. This is little gamma A and little gamma B. Okay, so if you have this kind, if you find a set of solution in which, in general, whenever this is taught in class, for those of you who haven't seen explicitly what these matrices look like. Any quantum field theory textbook will have these matrices. So these are called the Dirac matrices. So if you have any matrices that satisfy this anti-commutation relation, then using these matrices, you can construct an NAB that will satisfy this commutation relation. And therefore, the solution that you get for the Dirac matrices are another representation. This kind of representation describes, as I mentioned, spin one or half integer spin states. Once again, for example, for the electron, for quarks, for neutrinos, these things are all transformed under this. Okay, and therefore you actually need to have. Therefore, if you're talking about, for example, particle physics or standard model combined with gravity, you need to understand how to write things, these objects coupled to, for example, how to write covariant derivative acting on it. And if you only have the Christoffel symbol, you have no idea how you're going to couple these things to these spin one half things to the Christoffel symbol. So therefore, if you just stick with the usual differential geometry, that kind of formulation becomes insufficient to describe these kinds of degrees of freedom, which is precisely the reason that we are discussing that we're discussing in this kind of formulation, which is in a sense much more general, because here I'm just saying that the covariant derivative will have the spin connection multiplying by the Lorentz generator, where the Lorentz generator can take any representation. So this doesn't prefer any representation over any other. So this is valid for any representation of the Lorentz group. Okay. Is there any questions with this long discussion? Okay. If not, then let's just move on. So let me just erase this, so this will not be important. Well, not important, but not relevant for what we. Oh, okay. Yeah, it's not relevant for what we're going to discuss. All right, so good. We have the spin connection. So importantly, so as you keep hearing me mentioning over. Okay, there's some. I guess there's something. Okay, so there's as you keep hearing me mentioning that there's curve indices and flat indices. So what I mean precisely is these things that we've introduced, which is the Vierbeins, which of course is a German word. And so this Vierbein, just to recap what I said before, is really because the gauge symmetry that we're talking about is local Lorentz symmetry as well as local translations. In other words, local Poincare symmetry. And the generators for local Lorentz is this is the Lorentz generator. But we know the translation is this guy. This guy is translation. So we know that whenever you talk about when we're trying to construct the covariant derivative, we always have the notion that the covariant derivative is always given by the usual derivative plus the gauge field. Let me write gauge field, or the connection, multiply by the generator. So in this context, you see that indeed, sorry, let me just check one thing. Okay, so in this context, you see that indeed here you have the Lorentz generator and you have the spin connection. So you see that the spin connection is actually the gauge field for the Lorentz generator. Now, what is special about GR, or what is special about this kind of the gauge system that we're talking about, is that for translation, the generator is also a derivative. So the generator is the same thing as the derivative. Okay. Therefore, we write the combination. So in principle, I should have had a gauge field multiplied by a derivative, but because I'm defining the covariant derivative to begin with, so I just combine everything into this factor here, where you will have the notion that generically you can perturb the EA mu as delta A mu plus, let me call this E tilde A mu. So that if I write it in this form, then you see that the covariant derivative delta A then becomes just partial A, something like partial A plus E tilde A mu partial mu. And therefore this will demonstrate that indeed there's a gauge field multiplying by the generator of translation. Okay. But this actually makes sense also in a different context, which is that you have, as we mentioned before, that these Vierbeins, there's actually a physical picture, or probably more connected to the usual way of thinking about things in Riemannian geometry, which is that that on the manifold, and so remember, what is a manifold? A manifold is that you have some space, and on this manifold, anywhere locally at any point, this is like Rn. Right, so at any point, at any local point, this is flat. So that's what we call the manifold. Just to once, I guess we've discussed this before in class, but just to remind you. So for example, in one dimension, the only manifold you have is just a circle and a straight line. This is the only manifolds that you have in one dimension. This is not a manifold. This is not a manifold because here, even though here locally, this looks like R1, but here at this intersection point is no longer, this is not R1. Therefore, this kind of object do not define a one-dimension manifold. Okay, so when we're talking about a manifold, which is what you've been doing in the beginning of this course, as you've learned that you're talking about an object which always locally is always locally flat. So if it's locally flat, that means we can draw pictures. That means that we can locally set up coordinates, orthogonal coordinate system. So since this is locally flat, so that means locally you can set up coordinate system where in this coordinate system locally you have something like eta AB, which is the flat metric locally because it's Rn, right? So the metric for Rn is just eta AB. Okay, so that's what I mean by flat indices. So flat indices are always defined locally. So locally at a point I can here at this point I can set up another set of orthogonal coordinates, and then I also have A, B. Yeah, so then I also have an eta AB here. So every point on this manifold, I can set up my preferred coordinate axes. Of course, as you know, that the orthogonal coordinate axes at different points will not be the same because the manifold is curved. Therefore, that is what EA mu means. So EA mu of x tells you that at any point on the manifold, what exactly. So of course, mu is the direction of the coordinate chart. For example, if you have some x coordinate chart here, then this is just telling you how the direction of the x coordinate chart relate to your local flat coordinates. Okay, so EA mu is like a set of sticks that you set up locally, and of course it's a function of x. It's a function of x because it depends on what position you are on the manifold. And therefore, this expansion also makes sense because you know that at any point you essentially just have you just have the usual eta or delta. At any point you have the usual delta, and then as you move a little bit away of that point, you have some x-dependent function, which tells you how the stakes that you set up should change as you move slightly away. Okay, so there's two explanations which they're basically complementary of what EA mu is. One explanation is the gauge field. It contains the gauge field of translation connection. On the other language, this is just that this is the coordinate, the orthogonal coordinate chart that you set up at each independent point. And therefore, you can, as we mentioned before, you can relate EA mu to your usual metric, since what is the metric? So the metric is what you see locally at different points. Therefore, you can set up that G mu nu is what? Is literally just G mu mu x is just eta A mu eta B nu contract with sorry, E, not eta. So this is the relation between the Vierbein and the metric. Okay, so this is the relation. If you really prefer to think about things in terms of Riemannian geometry, then this is the relation between the Vierbein and the metric. Okay. Okay, so this is and actually, if you go deeper, I don't know if any of you who've gone into this more. Then this will, because I'm using connections, and then this of course has natural language in terms of bundles, and so these are really well established structures of mathematics. So this is not something that we're just cooking up here, but these things all have a nice physical understanding in terms of why we introduced them. Okay, so therefore, since there's a difference between curve and flat indices, so in other words, so we can so this also makes us so this introducing this Vierbein also allows us to translate between curve and flat indices objects. So for example, I can have, if I have something that is, let's say some VA that is defined in flat indices, I can just multiply this. I can just multiply by the inverse of my Vierbein. So this is the inverse Vierbein. I mean, this is essentially a 4x4 matrix, right? So that you would expect that there's an inverse. So you can have the inverse of your Vierbein, and then this gives you the curl, the way that this gives you the how this vector looks like in curve indices. And you can do the opposite. You can have E mu A acting on V mu and then convert this to flat indices. Okay, and of course E mu A is the inverse, therefore this multiply by E mu B is going to be delta AB. So this is just the inverse. This is the inverse of your usual Vierbein. Okay, so now you see that why this is useful. So that means that we can just pretend, we can just do everything in flat space, pretend there's no GR, there's no curve background, we're not in curve space. So we just formulate everything in flat space, which is what we usually do in physics. And then at the end of the day, we just formulate everything in flat. And at the end of the day, we just use this Vierbein to convert it to take into the account that we're actually on a curve manifold. Okay, and that makes things very simple. Okay, and which is why we're, another reason why we're introducing this. Okay, good. Now, once again, so now that we've established the curve indice, flat indice, what is the point of the Vierbein, and of course we've also established previously why we want to have covariant derivatives. And now you see that since this, you see that why do we define things in this way now? Precisely because you're defining it through covariant derivative. The thing on the right-hand side must be also covariant, because if you, after a gauge transformation, so of course after a gauge transformation, so after this gauge transformation, delta A, delta B commutator will of course become exponential lambda delta A delta B exponential minus lambda, right? So this is a covariant object. If the covariant derivative is a covariant, then under gauge transformation, the commutator will also be covariant. Now, if you don't really understand what does the word covariant means, it's not important at this point. All that it means to us is just that under gauge transformation, the objects transform in a very simple manner. Okay, you can just use this as your definition. So just that you use this as your definition of what covariant means. It's just under the symmetry transformation, this object transforms in a very nice way. Okay. And since this transform in this fashion, therefore this is an equality sign. Therefore, therefore the objects on your right-hand side must also transform covariantly. So you can immediately conclude that DABC will transform as exponential lambda DABC exponential minus lambda. And also RABCD, which as I've mentioned last time, is actually our Riemann tensor, will also transform as lambda ABCD. Okay, and that is why we want to use to first develop covariant derivatives, because once you develop covariant derivatives, you can now define various different objects that actually transform covariantly under your transformation. And once again, the reason that you're doing this is because I mean, the ultimate goal that we're trying to do here is to write down an action, a Lagrangian, which is invariant under the gauge transformation, under these transformations. We want things to be invariant under the transformation. So in order for things to be invariant under the transformation, we first need to construct things which transforms very simple, in a very simple manner. And once we do that, then we can write down things which are actually invariant. Okay, so said in another way, to get invariant actions, to get invariant action, to get gauge invariant actions, one first construct gauge covariant building blocks. Let me use building blocks. Okay, so this is the standard format. This is the standard point of when we're talking about gauge. We talk about gauge symmetries. Okay. Okay. So we've established that we can generate the Riemann tensor and what we'll call this is called the torsion. Okay, and of course we can write them out. So if we write them out explicitly, so let me just write them out. So TABC, so you can just do this computation and map to the right-hand side. Then you'll see that this object that you define here, minus is given in this form. Yeah. Yes, this should be C. Good. Okay, so this is how the torsion actually looks like in terms of spin connection and the Vierbein. So of course I have my spin connection here. So can someone tell me why? I mean, so I have my spin connection defined like this. So what is why do I have it? I mean, so what is the definition for this with the curl with the nu? Because this is in terms of A, B, C, D. These are flat indices. So how do I go from this to this? Can someone answer?
Contrary within all of your body.
Yeah, exactly. So you just so this just to make sure that so this DC is just given by E nu A omega A, the inverse Vierbein DC. Okay. Just to state the obvious. And of course, you can also identify the Riemann tensor, and the Riemann tensor will be sorry, let me just use the same color. So the Riemann tensor A, B, C, D will then once you work out the algebra, it's just given by E A mu E B nu partial mu omega nu C D plus omega mu omega nu antisymmetrized and CE ED. Okay, so this is how the Riemann tensor and the torsion look like. For those of you who have good memories, or for those of you who don't, that's okay. You can just look at the video. You will notice that this form, when I write it in this form, this looks like the non-abelian gauge symmetry we have. The non-abelian previously when we talk in this course, when we first started with the U1 gauge symmetry and construct the field strength, then we generalize the U1 symmetry to non-abelian symmetries, which now the group symmetry that you have do no longer commute. And there we see that the field strength will have these terms. Now you see that actually, indeed, this Riemann tensor is actually a field strength. It looks exactly like the non-abelian field strength that we have. And this is not surprising because indeed, the Riemann tensor is just the non-abelian field strength of your local Lorentz transformation. Okay, so as you see that this is just the field strength of your omega, the gauge field, which is omega, which is the gauge field of your local Lorentz transformation. Okay, and in fact, you can even simplify this. So let's just since we can convert these indices, we can convert these indices to flat indices, to curve indices by multiplying with the inverse Vierbein. So if we multiply by the inverse Vierbein, we will immediately have that R mu nu, so we can convert it immediately to T mu nu C. So just multiply the inverse of this is just minus delta mu E nu C plus E mu D omega nu D C. And similarly, R mu nu CD is just, I'm just rewriting the same equations again, but just to do, I'm trying to do things a little bit slower so that everybody can really follow what's going on. Okay. So this is so now this becomes very simple. And in fact, if I define the covariant derivative as equal to, in the curl indices, as E mu A multiplied by delta A, the inverse Vierbein multiplied by delta A, then I see that this is literally just partial mu plus 1/2 omega mu AB MBA. And in this form, so in this form, then T mu nu is extremely simple. T mu C is just minus the covariant derivative acting on E nu C, and R mu nu AB is just it's just going to be sorry. R mu nu AB and BA is just going to be equals 2 times the commutator of the covariant derivative. Okay, so this is, I want you to show, just work out this. So this will be homework 1. So this is, there's going to be the last 2 homework today. So this is homework 1, which is that starting from this equation, which is how we define the Riemann tensor and the torsion in this frame. But of course, I've already given you that if you work out this equation, the Riemann tensor and the torsion and the Riemann tensor in terms of Vierbein will look like this. Then I just want you to show that if you define your covariant derivative in this form, then this equation simplifies to just the covariant, the anti-commutator of the covariant derivative is just 1/2 the Riemann tensor multiplied by the generator of the Lorentz group. Okay, so this is just homework 1. So of course, what you're supposed to see is that the torsion part actually drops out in this commutation relation. Okay, so of course, this is extremely enlightening, because in this form, remember that previously in local gauge symmetry, remember that we were talking about local non-gauge symmetry. Sorry, this is literally redundant in that I'm writing local gauge symmetry. This is local symmetry is gauge symmetry, so this is literally redundant. But what I meant is that we're looking at internal gauge symmetry, not local. meaning that these are not space-time gauge symmetries, remember. And we have the covariant derivative there, so there's no GR, we just have the covariant derivative, where the covariant derivative is just I A mu A times the generator of the group that you have. And then we just have that the gamma mu commutator is given by the F mu nu A TA, if you remember. We had something like this before, and where F mu nu now becomes F mu mu, if you write this out, is just partial mu A nu A anti-commutator plus, if you remember, FBCA A mu A nu B and C. So just something, might be some plus or minus sign with some I factor here, but this is the form that you have. Now you can compare this to here. So we have that, this relation here. So now we write out, let me just bring it back here. So now we have in our language in GR, we have partial mu, partial nu, where these are the gravitational covariant derivative, where it's just partial mu plus 1/2 omega mu AB MBA, where this is the Lorentz generator. And this commutator is just R mu nu AB MBA 1/2. So you see that this is exactly the same as what you do in field theory, right? Where once again you just have some local, you're having this gauge symmetry generator, you're making this a local symmetry, and you define your field strength through this commutation relation. Here you're exactly doing the same thing. And so now you see that the R mu nu AB, the Riemann tensor, is literally exactly the same as the field strength in gauge theory. It's just defined, it's just that you're using different symbol. I could have used F here just to be consistent. Okay, but these are literally exactly the same thing. Okay. Okay, so I just wanted to point this out. Therefore, so let's just continue. Actually, in this kind of language, so just a side comment. So in this kind of language, so once again, fundamentally, what is fundamental important is the covariant derivative, or you can once again we write it in the flats. In terms of flat indices, then we have A, B, C, and B, C, and C, B. So we can either use this or this form. So previously, for example, in Riemannian geometry, if you have symmetry or isometries of your manifold, we know that there's killing vectors. Here you can also have killing vectors, but instead of killing vectors, we're usually defined it as killing forms. And killing forms are just the statement that you have some vector field K that commutes with your for example, let me just use flat space coordinate. So these are that's what define the killing forms. And then you just have K, you can expand K on once again on the covariant derivatives. So you're going to have these two fields. And by going through the commutator, you'll see that this field will be determined in terms of this field. And once you have this field, and this, once again, these fields are determined by the zero of the commutator, and therefore it depends on your Vierbein. So the usual, in the original Riemannian geometry formulation of GR, you have the killing vector. Here you also exactly have the same thing. And these are just vectors who are covariantly constant. So since these are covariant derivative, the commutator of the covariant derivative with the vector are zero. So these are just killing forms or killing vectors are just covariantly constant fields. Okay. Okay, great. Is there any questions? Okay. If there's no questions, is there a question? Did I miss someone? Okay. So if there's no question, let's continue to move on. So let's see. Let's give a tally of what we have so far. So what we have so far is we have the covariant derivative. We've introduced two sets of gauge fields. First is the spin connection. The other is the Vierbein. We also have two sets of gauge symmetry. One gauge symmetry is, so remember that this, which I should have discussed before. So remember that once again, sorry for keep repeating myself, but I just want everybody to follow closely. So the covariant derivative transform, sorry, let me use flattened indices, transform as exponential lambda, delta A, exponential minus lambda. And the important point is that this lambda, or I forgot last time, did I use big G? Maybe I used big G last time. But I mean, anyway, so these things are just equal to lambda mu x partial mu plus lambda ABX MBA 1/2. Okay, so these are the gauge parameters. So these are the gauge symmetry parameter. Once again, if you're not familiar with gauge symmetry parameter, this is exactly the same thing as when you were talking about geometry, where you're talking about the diffeomorphism, where it means that, the very fact that you're defining objects which are independent of coordinate transformation, therefore it must be independent under x going to, for example, it's independent under x mu becoming, for example, c mu x, where this is the new coordinate system, and or infinitesimally, sorry, let me just write it in this way. So that means that x mu in an infinitesimal transformation becomes x mu plus some c mu x. Okay, so this is usually how we talk about coordinate invariance, which is it's invariant under x mu, so with going through a change where the change is defined as a function of x. This c mu x in the diffeomorphism is exactly this gauge transformation parameter, just using a different notation, but the idea is identically the same. Okay, so again, once again, we have the tally. Let's tally again. So we have the covariant derivative involving two gauge fields. Each gauge field is related to its own gauge parameter. So the Vierbein is related to the diffeomorphism, and the local Lorentz is related to the spin connection is related to the local Lorentz. Okay. So of course we expect that we can match things to our usual Riemannian geometry. So let's try to do that. And to do that, once again, whenever you have gauge symmetry, it's always a redundant. Okay, it's like, I mean, if I draw a picture, it's basically like the only thing you care is really this. Let's say if the only thing you care is really this. But then on the outside, you construct a bunch of construction. You embed this thing into a bigger construction. Okay, and most of these things is irrelevant to what you're interested in, and therefore, but sometimes it's useful because sometimes you can embed it in here, and then you can rotate this around and then remove these extra stuff to get what you want. And sometimes due to this rotation, things become more simple. So really, when you have a gauge symmetry, the gauge symmetry itself is a redundancy. I must stress over and over, is a redundancy. So the gauge symmetry itself does not really have much physical relevance, which means that we can just remove it. Okay, and as I mentioned before, so to remove the gauge symmetry, what you do is you fix a particular gauge. Okay. So now if we want to go back to the Riemannian geometry, so let's just remove, so in the remaining geometry, remember that in the remaining geometry, we really only talk about coordinate transformation. And since I already said that the coordinate transformation gets mapped into this lambda mu x, that means that the local Lorentz transformation should be removed. So let's remove the local Lorentz transformation. Okay. So in other words, to remove gauge redundancy, what do? We fix the gauge. So what does this mean? So for example, if the way that I'm formulating, so let's say if I'm in a building and the building has rotation invariance, right? So the building is just round, it's rotation invariance. So there's a redundancy. So if I go around the building, it's always the same. So I want to remove this redundancy. How do you remove this redundancy? You choose a point here and I say, oh, relative to the point, where is my position? Right. So you use a point to fix your orientation, and that removes this rotational symmetry because you have a fixed point in your description. So similarly, to remove gauge redundancy, we fix the gauge. So we find a particular configuration of our field, or we impose a particular impose that our field must satisfy some particular conditions. So to fix the gauge, that means we need some gauge condition. And here, so we need some gauge condition. So this is the usual format. So here, so now we're going to fix local Lorentz, the local Lorentz degree of freedom. And the gauge fixing condition, so the gauge fixing condition is that I'm going to write eta mu and A E B mu is 0. We use this as my gauge fixing condition. Okay, here eta mu A, even though eta is really defined as A, B, our usual flat indices, but here eta mu A is the same thing. It just means that when mu is 0, A must be 0. When mu is 1, A must be 1. Okay. So to understand why I'm using this as a gauge fixing condition, so remember my eta E B mu is really a flux. You can say that it's really defined around the flat space or around delta, right? So remember previously we had something like we wrote it like this. It always contained an E B mu thing, a delta thing. Okay. By the way, since it always contained a delta thing, so actually you can always define the determinant of E B mu. This is never 0 because of this delta piece. This thing is never 0. Actually, this thing will be extremely important. The determinant will be extremely important as we'll see soon. But let me not introduce that. So if I write it, so if I have this term here, so if you expand your Vierbein. If you expand your Vierbein in this way, then you see that indeed, so the reason that you would like to have this condition is just that the leading term, which is delta B mu, just gives you eta A B. And indeed, of course, in flat space, eta does not have the anti-symmetric component. It's always symmetric and actually diagonal. So indeed, in the flat space part, this is really 0. Okay, so that's why this is a natural gauge condition that you want to use to impose to constrain the function. Okay, so using this gauge condition, we can now remove local Lorentz transformation. So by removing, meaning that degrees of freedom is now just completely fixed by other things. To see this, remember that the transformation that you guys derive in your last homework, you should be able to derive that the variation of this under, and I mean, once again, in your last homework, the whole point of how the gauge field is supposed to transform, the gauge field is supposed to transform in such a way that the covariant derivative transform covariantly. That's fixed, that's by definition. But by definition, we want to define the covariant derivative which transform covariantly under the local transformation. And therefore the gauge field is there to ensure that this actually happens. Okay, and therefore the covariant property of the covariant derivative will determine how your gauge field transforms. And so in your homework, you're supposed to derive that this the variation of the Vierbein is given by you should derive this. Okay, so now since you derive, so once again, before moving on, and I already discussed this last time, but let me just say it again. So you see that under the lambda mu's, these are coordinate transformations. So you see that the variation of their Vierbein contains a term that is the derivative of the coordinate transformation, and this reflects the fact that my EA mu contains the gauge field for coordinate transformation. Okay, once again, the gauge field for whatever transformation you have, the variation of that gauge field will always contain the derivative of the parameter of that transformation. Good, but now we're not interested in local Lorentz. We're actually in the coordinate transform. We're actually interested in how it transforms under local Lorentz. So let's just stick this. Let's just stick this equation into here, and so the variation of eta mu a EB mu is of course going to be the variation of EB mu, and so, and then you can just plug this in here, and then the leading term will just become minus a half. Well, I mean, let's just write down the leading term. So by leading term, I'm meaning that so this is going to, okay, let's just write things out so that people can follow. Whoa, sorry, I keep writing the wrong thing. Okay, sorry, I'm just getting lazy. Of course, this is really B here, so I'm just erase this. This is B. Okay, okay, great. So this is the variation that we have. Now let's further expand this. So let's further expand EB mu in terms of delta B mu. Plus, let's say that, let me just call this E tilde, and drop these terms. And so I just want to keep the leading term. Then for the leading term, of course, then this term will be 0 because this derivative acting on the delta is just going to be 0. So you really only have these two terms here. Okay, you just only have these two terms, and therefore you're going to have equal to eta mu a times minus delta b nu partial nu lambda mu times lambda b c delta c mu. Okay, and therefore what you get is, in the end, you get minus a half, because it's anti-symmetric with b. Okay, so you have minus a half lambda a b plus partial a lambda b is equal to 0. Okay, so that means that to fix this gauge, now you see that lambda AB, the local Lorentz transformation, is now completely fixed. It's completely fixed in terms of the coordinate transformation. Okay, so this is, so now the local, indeed, so if I impose this gauge condition, my local Lorentz is going to be fixed by the vector gauge, the local coordinate transformation. Okay, good. So once again, remember previously we say that we have two gauge fields and two gauge symmetry. Now I've removed the local Lorentz using the gauge fixing. I'll remove the local Lorentz, and then all I have now is the coordinate transformation. But I'm not done. You can say that, hey, but don't I still have the gauge connection for the local Lorentz? How is so don't I have more degrees of freedom? Well, indeed you have, but these can also be removed. So so this is the punch. So importantly, so the spin connection degree of freedom can be removed by requiring that the torsion vanishes. The torsion is 0. Okay. In other words, I want TABC to be 0. This removes the spin connection. Okay. So remember, what is TABC? So TABC we've written down here. So this is TABC. So let's sorry. So let's copy and paste here. So this is our torsion. So let's come here. So this is our torsion. So you can already see that if I require that my torsion is 0, then this becomes 0. Then you can see that indeed, in principle, you can express your spin connection completely in terms of your Wehrbein. Okay, so once you set the torsion as 0, then the spin connection can be completely determined in terms of the Wehrbein. So for those, so of course, this is a standard discussion in GR. That's why in GR, we always talk about, in general, we talk about the torsionless formulation. And the reason we talk about torsionless is precisely because that this is necessary to remove the extra degrees of freedom that you have. So just to show you how this is removed, so let me just write this because this is standard. This is a standard derivation in the textbook. So basically, let me just lower this indices. So let me write TABC. By the way, if something that has flat upper indices, you can just use the metric, the flat metric, to lower it to lower indices. Okay, so it's very easy to raise and lower the flat indices. Okay, so is there a question? Okay, so let's see TABC. So we can write TABC. So let me just write this out. This will be let me write CABC plus omega ABC minus. Let me first write this equation out. So this is just a rewriting of this equation, where CABC is just minus E. Sorry. C. Okay, so this is just partial mu E nu of the inverse Wehrbein, and I'm just lowering this lower indices to C. Okay, and as you see that this is just nothing but this piece here. Okay, but importantly, of course, that this is antisymmetric. So CABC is antisymmetric in these two indices, whereas the omega, these are the spin connections. These are antisymmetric with respect to the last two indices. So that means that I can write, so let me just, since A, B, C, these are just dummy variables, let me just reorganize it. So let me just write another equation, just interchanging A, B, C. So let me just write the cyclic rotated version. And then CAB is equal to CAB plus omega CAB minus omega ACB. Okay, So once again, since this is antisymmetric, so let me just label this as equation 1, equation 2, and equation 3. Okay, so since this is antisymmetric in AC, this is antisymmetric in BC, we see that this is actually the same thing as this guy, since this is, so let me just write this as plus omega A BC, okay? And similarly, this is the opposite of this guy, so let me just write this as minus omega BAC, and this as plus omega CAB. Once again, this is antisymmetric. So then you see that if I have equation 1 plus equation 3 minus equation 2, so the minus of equation 2, the omega CAB, this can cancel with this guy. And the minus equation of omega BAC, this can cancel with this guy. They're the same sign, so these two can cancel. So then, so that means that, and since your torsion is, so that means that this will give you, of course, 2 times omega ABC. So this will give you 2 times omega ABC C ABC plus CB, sorry, plus CAB minus CBCA. This is going to be equal to a bunch of TABC plus TCAB minus TBCA. Now, importantly, I'm enforcing my torsion field to be 0. So these are all 0. So therefore, you have that omega ABC is just written in terms of these derivatives on the Vierbein, where this is defined here. So once again, the punchline is that the torsionless constraint, once you have the torsionless constraint here, then you see that your omega ABC, the spin connection is completely written in terms of the derivative of the Vierbein. Okay, so this is the punchline. Okay, so now we've seen that by using the gauge fixing condition, we remove the Lorentz gauge symmetry or the Lorentz gauge transformation, and then with the torsionless constraint, the spin connection is also now written in terms of Vierbein. Okay, so our degrees of freedom are now drastically reduced. Okay, good. So we're almost there. So we're almost, so the end of this is to write down the Lagrangian and then to derive the Einstein equation from it. Okay, so so now we're able to remove the Vierbein and remove the spin connection in terms of the Vierbein as well as the torsion. And therefore, we can immediately write down. So first of all, once again, since everything is in terms of Jacobi identities, everything is in terms of covariant derivatives, we have that now the original algebra where delta A and delta B gives you, but now because we're imposing that the torsion is 0, so now we only have R, A, B, C, D, and DC. Okay. Therefore, you have this condition, and since RABCD is defined from the covariant derivative, I think I mentioned this in class, we know that from the Jacobi identity, which is that delta A, delta B, delta C, plus the cyclic image is 0. We know that this is an identity that is 0, but we also know that the two delta A, delta B The commutator is RABCD times MDC. So this immediately gives you two conditions. So the first condition is that R totally antisymmetric ABC D is 0. And then the delta A R B C D E is 0. So you get two conditions. Okay. So this is homework 2, which is actually I've simplified things. So I'm already imposing the torsionless constraint. So starting from this definition, show that from the Jacobi identity, you get these two conditions. Okay. The way that you do this is very simple. It's simply just commuting through the algebra using this definition, and then you'll get two sets of equations. The reason that you get two sets of equation is because after doing this on the left-hand side, so if you actually plug this into here on the left-hand side, you're going to get something that is, let me call it A times MBC plus B times on delta A. Okay, and so therefore A and B are separately equal to 0, and that's why you have two conditions. Okay, so this is homework 2. And from this homework 2, you'll realize that actually RABC, since R antisymmetric, so let's just write what this means. So A, B, C, D, I'm just going to lower this indices using the flat eta. So this is saying RABCD plus BCAD plus R CABD is 0. Okay, this equation just means this. But from this, you can immediately see. So first of all, of course, I can just antisymmetric this guy. Sorry, since by the way, from here you already know. So you have this equation, but previously you also know that RABCD is minus RBACD. So it is antisymmetric with the first two indices because of this defining equation here. So it is obviously antisymmetric with respect to AB, and also RABCD is antisymmetric with respect to the last two indices because it's multiplying by the Lorentz generator where this thing is antisymmetric. Okay, so now these two things combined with this, now you can, for example, I can write A, B, D, C. I'm just replacing A, B, C, D and replacing C, D with D, C. I can now immediately write down another equation, which is B, D, AC plus RDABC. This also, if this has to be 0, then this obviously has to be 0 because ABCD doesn't mean anything. I can choose ABCD to be whatever it is. All right, so you have these two equations. If these two equations are separately 0, I can add them together. I can just add them together. But you know that ABDC is going to cancel ABCD because it's antisymmetric. So these two guys are canceled. And therefore, you're going to, so adding these two equations together, you're going to get RBCAD, okay, minus RADBC, where I'm doing minus because I've exchanged DA into AD, okay, plus RCABD minus RBDCA has to be equal to 0, okay? And the reason I'm writing this is because in this fashion is because of course you can to rigorously prove this you have to consider more relations, but you can already see that there's a solution, which is that RBCAD is equal to RADBC. Okay, in other words, not only so in other words, the exchange of BC with AD is the same. So the Riemann tensor is the same under the exchange between AC and BD. Okay. So in other words, just to write everything in terms of words, the torsionless constraint plus Jacobi identity tells you that RABCD, the Riemann tensor, is symmetric under the exchange of the first two and the last two indices. Okay, so this is a consequence of the Jacobi identity as well as the torsionless constraint. Okay, so as those of you who follow the course know, so now I've fully reproduced all the symmetry structure of the Riemann tensor. Okay, once again, the Riemann tensor should be antisymmetric with the first two indices as well as the last two indices. Okay, it's antisymmetric with the first two indices because of because from the defining representation, the defining equation, you already see that it's antisymmetric with respect to the first two indices. It's also antisymmetric with respect to the last two indices because, again, from the defined this definition, because it's multiplying by the Lorentz generator. But then adding torsionless constraint plus the Jacobi, the torsionless constraint is really what is extra. The Jacobi identity is just an identity that must hold whatever for any case. Then you also get that the exchange of the first two with the last two indices, you get the same thing. Okay. Good. So now we're close to the end. So we've constructed our Riemann tensor from once again the Riemann tensor from now you're able to express it completely in terms of Vierbeins to see, right? So we already defined the Riemann tensor in here where you have the Vierbein, you have the spin connection, but again because of the torsionless constraint, the spin connection is now also expressed in terms of derivative of the Vierbein. And therefore, we have now the Riemann tensor, which is now completely a function of Vierbein. And the Riemann tensor satisfy the symmetry properties that all of you know when you're doing things in Riemannian geometry. And so the next and the last thing is to just write down gauge invariant actions. Okay, and we're going to use Vierbein to write down the gauge invariant action. And we're also going to use the equation of motion for the Vierbein to derive the Einstein equation. Okay, so this is the last two remaining things that we're supposed to do. Okay, good. So I think this is a good point where we actually take a break. Is there any question?
Teacher,
Yeah.
why omega W is symmetry? Here, why the last two index can be changed?
No, it's not. It's antisymmetric. It's the same thing. It's the same reason as why the last two indices is antisymmetric for the Riemann tensor, because the spin connection is multiplied by the Lorentz generator, right? Since the Lorentz generator is antisymmetric with respect to these two indices exchange, the spin connection also has to. Is that okay?
Yeah.
If you have, I mean, said it another way. So if this is antisymmetric, then the symmetric piece. So first of all, you can always separate this into the symmetric piece and the antisymmetric piece, right? Do you agree?
Yes.
Now, since this is antisymmetric, the antisymmetric multiplying the symmetric piece will be 0.
Ooh.
Right?
Yeah.
And therefore, all that you're left is the antisymmetric piece. So that's why I say that this is antisymmetric.
Okay, thank you.
Okay. So anytime you have something that is multiplying something that is antisymmetric, that means that the original thing is also antisymmetric, because even if it has a symmetric piece, it's multiplying 0. Right? It just becomes 0. Do you guys see what I'm saying? So let me just so this is just something. So if I have XAB times MAB, and I know that MAB is antisymmetric, then that means that XAB has to be antisymmetric as well. So let's say if XAB is not antisymmetric, it's just some random XAB, then I can separate XAB into XAB minus XBA, right? Plus 1/2 XAB plus BA, right? I can write it like this. Now I have XAB multiplied by MAB. So I multiplied this by MAB. Since this is antisymmetric and this is symmetric, this term will be 0, right? So you're left with the antisymmetric piece. So that means that XAB multiplied by MAB is equivalent to, let me just call X bar AB multiplied by MAB, where X bar AB is antisymmetric. It's just this guy. Okay, so whenever you're multiplying something that is with an antisymmetric piece, that means this guy is also antisymmetric. Is that okay?
Yes.
Okay. Is there another question? Okay, great. So we're at the final leg here. So we define everything covariantly. We project out the unwanted degrees of freedom. We're left with, again, the coordinate transformation. We have our Riemann tensor, and we have our Vierbein. Now we're ready to write the action that is gauge invariant. And from that action, we're going to derive the Einstein equation. Okay, so let's just take a 10 minutes break. It's 45. So let's come back at 55. All right. See you guys soon. Great. Okay, so this is the final leg of the semester. So everybody hanging tight. Good. So now that we've removed the extra Lorentz gauge condition, so now we're ready to write down the Lagrangian. So once again, we have the whole point is that we have covariant object. So let me just talk a little bit about this final thing, that the final building block that I have. So I'm going to define E, which is defined as the determinant of EA mu. Okay, so of course we, for those of you who are familiar with this, there's a formal definition. So let's just define this. So this is basically just E mu rho sigma, or epsilon A, B, C, D, where you have epsilon A mu, E, B mu, E, C rho, and E, D sigma. Okay, so I mean, this is just basically how you write down your determinant. Okay. For those of you who take apply math 1, you know this, and now you see that why I actually introduced in a very early age, because at an early time, because this actually comes up over and over as you work on different areas in physics. It's useful to know the proper definition of determinant for any dimension. Okay, good. So this is our determinant. Now I'm going to write the variation of my, so just some variation of E. Of course, this is just going to be written as E inverse variation of E, because this is just variation of long E. So the point is that, so I'm going to show that the variation of, so the variation of E, so let's see what is the variation of E. So the variation of E is the variation of the determinant, right? So that is given by the 1/4 epsilon mu nu rho sigma epsilon A, B, C, D, variation of E, B mu, E, B mu, E, C rho, E, D sigma, right? And all I'm doing is just variation. All I'm doing is just variation of this guy, and then of course you're gonna vary this plus vary this plus vary this plus vary this. But there's 4 terms, but they really are all identical because these are just dummy variables. So you get a factor of 4 that cancels with this 4 factorial here, and so you get this form here. Okay. Now if you look at this form, for those of you who are familiar, you note that the inverse. So remember that the inverse EA mu. What is the inverse? The inverse is is defined as the inverse EA mu is defined that it contract with E mu B is delta AB. That's what the inverse is defined, right? So this is the definition of the inverse. And if you know, if you've taken the course before, you know, or in applied math, you know that the inverse, another way of writing the inverse is precisely in this form, right? The inverse is, you can always also write it as 1/4 factorial epsilon nu rho mu nu rho sigma epsilon A B C D E B nu E C rho E D sigma. This is the inverse. Oh, sorry. And then of course you want to divide it by the determinant E, right? To see that this is the inverse is very simple. It's just because if you take this form and then multiply by this, you immediately get the numerator with the 1/4 factorial, you immediately get the determinant, and therefore it cancels with the E downstairs, and that gives you the identity. Okay, so this is the inverse. And therefore, since the variation looks like this, it looks exactly as the inverse, just without this E factor, right? And therefore, this tells you that the variation of E, okay, so the variation of E, so the variation of E, which is 1/4 factorial of this guy, is just equal to variation of E B mu, right, times E times the inverse. Right? It's just this, because the inverse is just 1/4 factorial with this guy, but with an extra factor of E. But this piece here is exactly the same as this piece here, but without the E. So you just have this extra factor of E here. Okay, but then said in another way, so these are just identities. Said in another way, so that means that E inverse variation of E is just equal to E mu B variation of E B mu. Okay, so that means that the variation of long E is just E mu A variation of E A mu. Okay. By the way, so this is actually this is one of the things I want to spend the last probably an last hour to really go through with you guys, which is that oftentimes it's in these, you can see that in these derivations, it seems like I'm pulling all sorts of tricks, right? For example, the variation of long E, I could have just gone inside and then just you know 土法炼钢, now to just take the determinant and then vary and then work through these things. But often in physics, it's more insightful to do these things to maintain as much of the structure as you have along the way of the computation, and not always just just blast things through with force, and in the intermediate stage you can generate a lot of errors. And more importantly, when you try to do things that just do it by brute force, oftentimes even if you get a result, the entire thing is not very enlightened. You just know that this is equal to this. You don't see what is happening, what is going on, but along the way, it's just, for you, it's just a straightforward calculation, and you're just working page by page and they're just calculating things. But besides getting the answer, you don't really learn anything during this long calculation. So it's often important to learn how to do things not by brute force, but rather by trying to maintain as much structure as possible along the way. Okay, good. So using this form, so using this kind of argument, you can immediately see that the variation of long E, the variation of long E is just E mu A variation of E A mu. Okay, so why do I write it in this form? Because I know what the variation of EA mu is, right? So we know what the gauge transformation is. Therefore, I can write. So let me just erase this. So this is not. We're not going to use this anymore. Okay, good. So this is the the variation, and we've seen what the variation. So let me just write it down instead of copy and paste. So remember that we have that the variation, the gauge transformation. So the gauge transformation of EA mu. So then this is just, once again, this is something that you derived last time. So let me see, where did I write it down? Yeah. Derived last time. So the variation of EA mu is just given by lambda nu partial nu EA mu minus EA mu partial nu lambda mu. Okay. Do anyone find funny what I've written here? Is there something missing here? I just written down the variation of my real body. Do any of you find it funny or weird? No? Everybody thinks it. What?
There's no and
It's what?
there's no and maybe and that's Lawrence.
Yes, or there's no lambda AB, right? There's no lambda AB term, right? So remember that previously I wrote this thing down. Remember? Now I dropped this. Can anyone tell me why I dropped this now?
Because of orthogonal property with EA mu.
EA mu. Yeah, okay. Because I don't know what you mean by orthogonal property, but I'm going to interpret it as you mean that we're already doing the gauge fixing. Right? Remember when we do the gauge fixing, right? Remember when we do the gauge, is this orthogonal property you're talking about?
Yeah.
Okay, so we're doing the gauge fixing. Okay, so once we do the gauge fixing, this is no longer this is completely fixed. So there's no longer such transformation anymore. Okay, so we're only looking at the local, so we don't care about this the spin connection transformation. It's all removed now. So with this, so we can plug, so now we can plug this transformation in. So this is now equal to EA mu lambda nu partial nu EA mu minus this multiplied by this is just the inverse, right? So this just becomes partial mu lambda mu. Okay. Now this term, once again, so this is actually very similar to before, right? So this is the derivative. So I claim that this term can be rewritten as lambda mu partial mu long E again, minus partial mu lambda mu. The reason that this is long E is, once again, it's the same argument as I gave before. It's just because the derivative hitting on long E is going to give you E derivative hitting on E, but then E is just a determinant. So this is just going to give you something that is the partial mu of EA something inside, let's say nu, but then the remaining thing is going to be the inverse. Okay, and then you can, and of course with this extra factor of E to compensate things, and therefore these two things are exactly the same. Okay, so for those of, so if you think that this is too fast, this is exactly the same statement I made before. So I encourage you to show that this is the same as this. Okay, in fact, let me just put this homework 3. Okay, show that this term is exactly the same thing as this term. I think if you just follow what I discussed before, you'll see that this is true immediately. Okay, once again, let me just go through to guide you through a little bit. So remember that partial mu long E is just E partial mu E, but then E is the determinant, so it's E partial mu. So it's once again all of these epsilon 4 factorial E B nu E C, well, blah blah blah, right? And so the derivative is going to hit on one of these, and it's going to remove this 4 factorial into 3 factorial, but then it's going to be partial mu E A nu, but the remaining thing is just going to be the inverse, and therefore you can just, and therefore it just, you just directly convert it back into here. It's the derivative of E A mu multiplied by the inverse. Okay, but I want you to go through the details and work things through closely. Okay, good. So you see that whenever you have variation, so that's also an important thing, is that whenever you have a variation of your metric, or sorry, a variation of a matrix, and then this variation is multiplied by the inverse, this thing can always be rewritten as just operations on your determinant. Okay, this is one of the nice fact about inverse, is that if you have if the inverse is coming along with the function itself, then this variation is always related to just the variation of determinants. Okay, good. So we've shown that so let's just recap. So we've shown that the variation of long E is given by lambda mu partial mu long E minus partial mu lambda mu. Okay. Therefore, we're going to be interested in, as you will see shortly, the variation of E inverse. Okay. The variation of E inverse, so this is going, you immediately see why I'm doing this, is going to be minus E squared variation of E, which is equal to minus E variation of long E. Okay, therefore this is just the variation of E minus lambda mu partial mu long E minus partial mu lambda mu, which is nothing but the total derivative acting. Okay, you can show this is the total derivative acting on lambda mu E inverse. Okay, so this is the important point. So once again, the gauge transformation of the inverse. So to take E as a, remember E is the determinant of your Vielbein. So E is the determinant of your Vielbein. Therefore, the determinant of your Vielbein, you take the variation of the inverse of this determinant is going to give you the total derivative acting on lambda mu E inverse. Now, once again, of course, you can just derive this directly by going through just, once again, 土法炼钢暴力下去, you just brute force and force it out, and you can derive this, but that's not very enlightening. If you do things this way, then everything is compact and can derive it in one page. And it's just given, so the variation of E inverse is just the total derivative. Okay? Okay, so what is the whole point of doing this? Well, that tells you that if you write your action, because remember, I mean, so we want, so remember, let's say we try to write an action. Let's say we want to try to write an action. So let's say if it's just dx4 with something here, where this is a scalar. Remember that in the very beginning, as we discussed before, any operator that is a function of x is not gauge invariant. It cannot be, because it's going to change under coordinate transformation. Even if this is just a scalar, we know that the variation of a scalar is going to be lambda mu partial mu acting on under the coordinate transformation, right? This is how a scalar transforms. Right? So that means that the variation of S, if I just write something like this, is just going to give you dx for dx for lambda mu partial mu OX, right? So this is not going to give you anything. So this variation is not gauge invariant because there's still this term here, right? So in order for you to gauge it, to write down a gauge invariant action, what you want to do is you want to say, hey, can I write something like this? Let me just call, let's say you dream that you can have a wish, you can have something here. And if this thing can be given by the variation of A, if it involves partial lambda times A plus lambda partial A, then the variation of S, which is going to be dx for, so it's going to be partial lambda A O plus lambda partial A O plus lambda A partial O, right? Because the O will transform in this form. Then this will take into, then this will, sorry, this is partial lambda A. Sorry, I should write it like this. Okay, then this is literally just a total derivative, lambda A O. Right? So if I can find some A, such a A transform in this fashion, partial lambda A plus lambda partial A, then this A multiplied by any scalar function or some scalar operator or whatever, anything that is scalar will result in a gauge invariant action. Okay, do everybody follow? Okay, remember, the problem with writing, so what you're trying to do is you're trying to write down an action that is invariant under the gauge symmetry, right? So if I want to write something down that is invariant under gauge symmetry, of course, we also need it to be invariant under Lorentz symmetry because this is Lorentz invariant. So naturally, you would write something that is scalar, but we know that scalars transform under coordinate transformation. Okay, you change the coordinate definition because it's the fact that this is a local operator is going to change. And it's going to change in this form. So if you just write something like this, like the action that is just an integral over some scalar operator, this is never going to be invariant under local coordinate transformation. So you need to have something here such that under gauge transformation, this will have the variation of lambda A and plus lambda partial A, then this thing here, then the action here will be invariant. Okay. Now you already see that, so the wish thing that you have here, so the wish, the thing that you wish, your Christmas present, is something that the variation of this thing must have the derivative of lambda plus lambda of A. The fact that you have the derivative of lambda, as I mentioned before, this is a derivative of your gauge transformation parameter. Therefore, this must be related to your gauge field of that gauge transformation, which is the Vielbein. So you already know that A must be related to, it must be a function of the Vielbein, right? And I have just given you exactly what that function is. So because we've already shown that previously that the variation of the inverse determinant of your Vielbein is given by the total derivative acting on the lambda, the variation parameter plus the inverse Vielbein itself. Okay, so that means that A is, so that means that we're finally here. So the first punchline, that means that our A is just E inverse. Okay, so in other words, if you write an action, which is just dx for, if you just dx for E inverse multiplied by any scalar operator x, this is invariant under lambda x transformation. In other words, this is variation of S is going to be equal to integrate dx for partial mu lambda mu e and sorry, partial mu. Maybe I should so it's a total derivative. Okay, so now we can write down anything we want here as long as it's a scalar operator. You just have to multiply it by the inverse determinant of your Vierbein, and that will be your invariant Lagrangian. And precisely this inverse E inverse is precisely the square root minus G. Okay, because remember that G mu nu, what is G mu nu? G mu nu is just E mu A E and nu B eta A B, right? So if you take the determinant of G mu nu, you're going to get the product of determinants of these E's. Where notice that these E's are inverse Vierbeins. Okay, and therefore the square root is just going to give you this, is just going to give you this, the inverse Vierbein itself, the determinant of the inverse Vierbein itself, which is why you get the e to the -1. Okay, but now you also see why using Vierbein is much more natural than using the usual Riemannian geometry, because in usual Riemannian geometry, you need to introduce the square root. Okay, you write down minus square root G, blah, blah, blah stuff. You have this weird square root, which makes you worried because it makes you think that, hey, there might be something subtle with the branch cut. Is there going to be branch cut with your G, when your G, you're trying analytic continue from one analytic region of G to some other, then there's going to be branch cut continue, and then you might cause this wonder. But if you write everything in terms of Vierbein, there's no branch cut. I mean, it's just a determinant. You're just doing the inverse determinant, or the determinant of your inverse Vierbein. It's the same thing. Okay, good. So we have our punchline. So after all of this, then the invariant action under local coordinate transformation is always written as dx for e to the -1, which is the determinant of the inverse Vierbein, multiplied by any scalar function that you like. And this will be an invariant action for local coordinate transformation. Okay, good. Now, what are the, so if we just have the Vierbeins and if we just have the Vierbeins and nothing else, we don't have any matter fields or anything. So what are the actions that we can write down? So that means that the action that we can write down, of course, but still we need this to be a scalar, right? So of course, the action that we can write down is, let's say we can write down, well, we can write down the trivial thing, which is just e -1, and let's just time some constant. So this is just some constant. This is obviously invariant under local coordinate transformation, and in fact we can have this. Now, if we just have the Vierbein, then the previous thing we've shown that we can have is, of course, you can have the Riemann tensor, right? But then so you can have the Riemann tensor, but now you need it to be a scalar, right? So the first non-trivial thing you can write down is just write the Riemann tensor. So let's put lambda. Let's plot the Riemann tensor A, B, C, D, but it needs to be a scalar. That means that I want to contract these A, B, C, D with the metric, the flat space metric, because everything is in flat space. In order to contract with of course, I cannot contract these two or these two, because we just mentioned before that contracting these two are antisymmetric, so you cannot contract with eta. So the only thing you can contract with is to contract with delta CA, for example, delta dB. And this, as all of you know, this exactly gives you the Ricci scalar. Okay, and therefore the simplest the simplest coordinate invariant action that you can have is just lambda plus Ricci scalar. Of course, you can add more terms here, which involves more powers of Riemann tensor or Ricci scalar. But those are higher order terms. So this is just for the leading term, you can have these two. And so now we've seen that we have the Einstein-Hilbert action. And this is, of course, the cosmological constant. Okay. Any questions? Okay, good. Great. So we're finding here, we're at we've re-derived starting from this entire gauge symmetry, gauge invariant discussion. We finally arrived at the Einstein-Hilbert action. The only thing left now, so of course this is not this, we can say that this is just deriving what we know before. So the only thing left is just that. So of course this is slightly different than what you're used to. What you're used to is you have dx for square root minus gr, where this r is a function of g. Now instead you have e minus 1 variation, and this r is a function of e. But as I said, for many different reasons, that this is actually a more natural way to write things. So the final thing is, if I really want to, I should do the variation of this action, or maybe just even the Einstein-Hilbert action, and compute the field equation with respect to E, and then show that you can actually derive the Einstein equation. Of course, you should, but we can just do it as our great finale. So we're going to rederive Einstein equation. Okay. So let's derive Einstein equation. So let's derive Einstein equation from the equation of motion of E a mu, the Vierbein, from E inverse R of E. Okay. Okay, so to facilitate my, I'm going to call, so once again, we're gonna, so this is, so let's say that this is, so this will be our Lagrangian. So this is our Lagrangian. So we're gonna vary our Lagrangian, and we're gonna vary by varying EA mu. Okay, so but I like to maintain things to be in flat indices. So I'm going to, once again, so I'm not going to brute, of course you can, once again, you can brute force and compute the variation of EA mu and derive the variation of Lagrangian here, but as I mentioned, that's not very insightful. So what I'm going to do is I'm going to define an object called XAB. Okay, that's just going to be, it's very related to EA mu, but I'm going to contract it with an inverse Vierbein. Okay, therefore, I mean, since this is inverse Vierbein, so of course, so this is defined, my XAB is just defined as this. Okay, so it's still the variation of my field, but I'm just multiplying that variation with some factor. This will make the derivation much more smoother. Okay, and of course, if you have this, then if you want if you really prefer the original thing, the variation of your Vierbein, that you can always just get it by XAB and then EB mu. Just multiply by the Vierbein to get the original thing. Okay, so if I define XAB like this, then I can let me write this. So for example, so first, since so I'm going to, the most important thing is, of course, I need to know what the variation of my Ricci scalar is. Since my Ricci scalar is defined from the Riemann tensor, I should first derive the variation of the Riemann tensor. And since the variation of the Riemann tensor is defined with respect to the covariant derivative, therefore I want to derive the variation of the covariant derivative. Okay, so let's derive the variation of the covariant derivative. So let's do the variation covariant derivative, which of course involves EA mu partial mu plus 1/2 variation of the spin connection BC and BC. Okay, now I'm going to use XAB instead. Therefore, this I can rewrite this as X AB delta B. And then whatever this since this variation is just going to relate it to my XAB, I'm just going to call it for now. Let me just call it YABC. And then I'm going to show that YABC is going to be a function of X, since my spin connection is a function of my VO bar. But I'm just going to put a placeholder here for now. Okay, good. Okie dokie. Good. So since remember that in the torsionless limit, so in the torsionless limit, or under the torsionless constraint, I have delta A delta B, the covariant derivatives is equal to 1/2 RABCD MDC. Therefore, from this you can derive the variation of RABC, right? So variation of RABCD MDC is going to be equal the variation of your covariant derivative, right? So it's going to be equal to delta anti-commutator variation of delta B. Okay, so what this means is this is delta A variation delta B minus delta B variation delta A. So okay, so this is what this means. Okay, but we don't. I'm just writing it in a compact form. Okay. So since you know what, so I've already written this thing down here, what the variation of my covariant derivative is. I just need to plug it into here and then just expand the commutator. So if you expand the commutator, it is going to be equal to, let me just write down the result after the expansion. So it's just going to equal to delta A X B C delta C minus 1/2 X A C R B C D E M E D plus 1/2 delta A X B C D M D C plus Y. Sorry, this is Y. This is not X. So of course, this is Y. Plus Y A B C delta C. Okay. Now, on the left-hand side, so here this is nothing. This is just this plug in here, and then you're expanding out. So of course, this is an equality. You have an equality here and an equality here. Therefore, you identify the variation of RABCD with whatever is multiplying by the Lorentz generator. So you see that the variation of RABCD is given by this guy plus this guy. Now, you notice that there's no delta stuff on the left-hand side, right? There's no delta stuff on the left-hand side. And that's because you impose a torsionless constraint. Therefore, the torsionless constraint is reflected in that the right-hand side, the YABC must cancel with the derivative on XBC, which is what I said before, that the transformation here, which I just call it the variation of the spin connection, is completely determined by the variation of your VO bind, because we solved the spin connection in terms of VO bind through the torsionless constraint, right? And therefore, the fact that the torsionless constraint tells you that the left-hand side does not have any delta, will indeed reflect that in the right-hand side, the y-ABC is going to be given by the derivative of the x-BC. So by solving this, you immediately find, first of all, that y-ABC is, you can write down as a total antisymmetric piece, is just given by the covariant derivative acting on x. So this is BC A. And the variation of RABC. Now you have the variation of your Riemann tensor you derive. It's just delta A, YC, ABCD minus X, AERBECD. Okay, so this is the variation of your Riemann tensor in terms of y and x. Then y is also expressed in terms of derivative of x. Okay, so remember, so all I'm trying to do is just through the defining. So you see what I'm doing? I'm just using the definition of my Riemann tensor to derive the variation of my Riemann tensor under the change of my field of my Viobi. Okay, so after doing all this algebra, so let me just erase this. So all I need is just to write down at the end of the day the combined form. So after all this variation, so we can substitute the solution for y into x. Therefore, you derive that your variation of R A B C D is given by just 1/2 the anti-commutator of A, and I can write it the anti-commutator of C, but with XBD, where I, again, as always, I anti-symmetrize with respect to A, B, and also anti-symmetrize with respect to CD. Okay. And then minus 1/2 X, so this is X A E R B E C C D. Sorry, let me just write this out. So this is CD plus X C E R D E A B. Okay, so this is the change of your Riemann tensor. So this is the variation of your Riemann tensor with respect to, if you do variation with respect to your Viobi. Okay, and similarly, of course, we have the variation of we also need the variation of my inverse Vierbein, the determinant of the inverse Vierbein. And of course, we know that this is just equal to the variation of, once again, we can use this trick again, which is again just the variation of E, it's A mu variation E mu A, which is nothing but this. So now you also see why I defined this thing in the beginning, because then the variation of inverse, this is exactly the X that I'm talking about, right? So this is just minus E XAA. Okay, so now all I have to do is just contract this, and now I have to do is just contract this with delta functions, with the Kronecker delta, to make this into the Ricci scalar, and then I got the variation of the Ricci scalar. Okay, so putting everything together, so our grand finale, so the variation, the variation, where this variation is the variation of the Vierbein of E inverse R, is going to be equal to 2 times E inverse multiply, first of all, so let me just okay, so first of all, we have eta A B box minus delta A delta B minus RAB minus a half eta AB R multiplied by XAB. Okay, so the variation of your action is of course proportional to the variation of your field, right? Because this is proportional to the variation of your field multiplied by this factor here. You can immediately see that, for example, if eta AB contract with XAB, then you're going to have this 2 is going to cancel this plus a half, so it's just going to give you 1. So you get R times XAA, which is exactly this term that you have here, where you come from the variation of the inverse field by. So that means that the remaining terms are coming from the variation of your Riemann tensor or the Ricci scalar. Okay, so you see that this, of course, these are just derivatives. So the important point is this guy. So we see immediately that the equation of motion of your Einstein-Hilbert action with respect to now the only degree of freedom is your Vierbein, gives you the Einstein equation. So this is the Einstein equation. Okay, and that's basically the end. Okay, of course, there's many things we can talk about. We can talk about how to derive black hole solutions for the Vierbeins for the black hole solutions. We can really talk about how to couple things with spin to the Vierbein and so on and so forth. But just to let you have a flavor and just to let you see how these things in principle work, we see that and actually general relativity, you can just derive it by requiring that you have a local, that you have a gauge system where you have local gauge and local Lorentz symmetry, and then as well as local translation. In other words, GR is just a gauge theory of local Poincare symmetry. Okay, and if you want to say that why do we want to have gauge theories, is once again is because of the fact that we're talking about things that generate long-range forces which must be massless. And if something is massless, the degrees of freedom is always 2, which means that we need to introduce gauge symmetry to allow us to build something up that is redundant, that is redundant, but forms a representation of the Lorentz group. But then we can remove these redundancies. Okay, I think that's the end. So today we have 3 homeworks. And afterwards, later tonight, we're going to send us. And one of the homework previously, you've derived the linear perturbations of the metric, the linear perturbations of the metric around the short shell black hole background. So tonight we'll also give you the project, which is basically to just start from that, and you need to solve the equations of motion under certain boundary conditions. And I will tell you that one of these things that you solve will be related to the black hole tidal number, and you'll see that the solution to the differential equation actually leads to 0 tidal numbers. And that's what basically I'll write. And if you have any question, you can email me about the project. The due date for the project, as well as all of the homework, if you want to send in something late, will be Friday next week. Okay. Okay. Do we have any questions?
Yes.
Okay.
In the last equation, I don't see why the terms in the first parenthesis vanish. This is square eta AB squared minus.
Oh, it's not that they vanish. It's just that they're covariant derivatives. So these so okay. So once again, you want if these are like total derivatives, right? Because there's not oh, sorry. I should mention that yeah. So if you have something that is E minus 1, for example, actually maybe I should put this as a homework. But okay, if you have something that looks like this, sorry, no, I should have mentioned this. But actually I had to have this as a homework in mind. But if you have E inverse partial A, let's say some random VA, then this is completely equivalent to partial A E inverse VA. And therefore, these term, if you have anything that is of this term, it is a total derivative. Therefore, the variation of your action with these terms, which are all in terms of covariant derivative multiplied by E inverse, these are just total derivative terms.
Okay, thanks.
Okay, so yeah, so very nice. So actually, as you said, the invariance of, I mean, the invariance of the actions we really only need action to be invariant, and therefore the variation of your gauge symmetry sometimes will lead to that it's not really an invariant at the Lagrangian level, but the Lagrangian becomes a total derivative, and here, and the similar statement also applies to equation of motion, which is that when you vary things, if you got terms that are total derivatives, those terms don't contribute to the equation of motion. Okay. Okay, is there any other question? Okay, if not, then thanks a lot. This is it. If you have any more questions or things to discuss, you can send me emails. I will reply if I have as I have time. But unfortunately, we're in the lockdown period. So usually I would say that if you have any question, feel free to walk into my office. I am still in my office, but I guess you guys are not. So, yeah. So, but if you have any questions, feel free to email you. I'll try to respond as much as possible. Okay, thank you very much, guys.
对啊，老师有一个最后的问题。
Okay.
就是刚刚你说的 due 是 project 加上这次功课的 due 还是 project due？
就加这次功课，直接如果你想要迟交所有的功课，任何你之前还没交，你想要迟交的都可以交。
哦，cool，好，谢谢。
Yeah, yeah. So someone just asking that the due date is next Friday. That's for any homework as well as the project. Okay, 好，谢啦。